Hello. This brief video is intended to help with the one-map exercises, focusing on binomial distributions and the empirical rule. A binomial experiment is a particular type of experiment that meets the following four criteria. There has to be a fixed number of trials. Each trial has two and only two outcomes, for example, success or failure. The result from any one trial is independent of the results from every other trial. And finally, the probability for having an outcome which is a success for any given trial is the same. It's a fixed probability. Now, contextually, one way to think about this would be as a credentialing exam. On an exam, there are 80 items total. 68 are required to be correct in order to pass the exam. And the probability of a student passing the exam is 35%. A group of 40 students takes the exam. Now, if we think about this, assuming that the students are independent from each other, this would meet the criteria for a binomial experiment. There's a fixed number of trials, 40. There's a fixed probability of success, 35%. There's only two outcomes, pass or fail, and again, we've assumed independence. Now, to make sense of this though, first I encourage you to imagine that this is actually one group of 40 out of a very, very large collection of groups of 40. Say 1,000 groups of 40 students. Now the intuition for the binomial distribution is as follows. If we have a 35% success rate out of 40 examinees, we would expect that there would be 14 passes, which is 35% of 40. But the truth is we would not expect every group of 40 to have exactly 14 students passing the exam. We would expect some to have a bit fewer and some to have a bit more. For the binomial distribution, the number of passes out of groups of 40 examinees would have a nearly normal distribution. The average of that distribution would be what would be expected, which would be 14, the value we calculated before. But it would actually have a determinable spread, and that spread is determined by the formula n times p, the success rate, times 1 minus p, which is actually the fail rate, that product, and then you take the square root of that to get the standard deviation. Let me run a simulation to give a better sense of what I actually mean by this. Here's a brief amount of our code. The purpose of the code is to generate a data set of 1,000 values where each value is a group of 40 and the number of people who pass the exam from that group of 40. For our 1,000 groups, here's the frequency table. We notice that there are very few groups in which there were only 4 to 5 students passing the exam. In fact, there's only one group out of 1,000. Likewise, there were only 6 groups in which 22 to 23 students passed the exam. A histogram might be a better representation of this, and we see the histogram of the successful students passing the exam is nearly normal. And if we were to actually calculate by hand the mean and standard deviation of our 1,000 groups from the data simulation, we see that the values are close to what we expected. The average is about 14, and the standard deviation is about 3. Because the distribution of counts of passing examinees is nearly normal, we can apply the empirical rule that we learned about earlier. For example, we can estimate the percentage of groups that will have a given number of successes. The algorithmic process for this is built on the following formulas. For groups of size n with a success rate of p, the percentage of the time will provide us what we call critical value, and that critical value, z star, is simply the number of standard deviations above or below the mean in which we would expect to find that given percent. Now the formula that we have, as before, we use the mean and the standard deviation. Mu, the mean, is n times p. The standard deviation, sigma, is the product, n times p times 1 minus p, and we take the square root of that. The range is then found by taking the critical value number of standard deviations above and below the mean. In this case, the bracket notation here indicates that for the lowest value of the range, we always round up or into the interval, and for the highest value obtained, we always round down or into the interval. Let's look at an example. For groups of size 40 with a success rate of 35%, 98% of the time, the number of successes will be within 2 1/3 standard deviations of the mean. So our critical value is 7/3. And again, that value 2 1/3 comes from the empirical rule, the off-thirds empirical rule particularly. We're using the mean, we have 14. The standard deviation is calculated before is 3.02. And if we ask how many values fall within 7/3 of a standard deviation of the mean, we would multiply 3.02 times 7/3, subtract that value from 14, and add that value to 14. That gives us 6.95 for the lower bound, which we will round up to 7, and 21.05, which we will round down to 21. So the range of usual values that we would expect to see for the number of passes for this credentialing exam of 40 students would be between 7 and 21. More specifically, 98% of the time, if you had a group of 40 taking the exam, between 7 and 21 of them would pass the exam. Let's look at another example. A multiple choice quiz has 10 questions. Each question has 4 possible answers provided, of which only 1 is correct. So it would be unusual to get how many or more questions correct simply by guessing alone. How can we justifiably determine what this number is that we're looking for? First, let's set a reasonable cutoff for unusual, say occurring 2.5% of the time or less. Now we estimate a critical value for this percentage using an empirical rule. Well, if there's 2.5% at the upper end, which we're considering unusual, there'd be a comparable 2.5% at the lower end. That would give us 5% unusual values, and 95% of the values would be considered usual. Well, we know from the standard empirical rule that 95% of the values fall within 2 standard deviations above and below the mean. So that will be the critical value that we will use for this calculation. Now we'll use the algorithm to find the upper boundary of the interval of usual values. There are 10 multiple choice questions. There's 4 options for each question, so by guessing alone, there's a 25% chance of guessing the correct answer. So the average number of correct answers we would expect to see would be about 2.5. The standard deviation, multiplying 2.5 by 0.75, or 75%, we get the value 1.875, the square root of which is about 1.37. So we want to know 2 standard deviations above the mean, or 2 times 1.37 above the mean of 2.5, is the value 5.24. And that would be the boundary for the usual values, the upper boundary for usual values in particular. So we would round that value down to 5. Thus, 5 or more correct answers would be considered rare or unusual. Now, there's an inherent subjectivity here. Unusual here was defined as occurring less than 2.5% of the time, or we could think of that as saying it occurs 1 out of 40 times. If something occurs less than 1 out of 40 times, it's unusual. And is it fair to ask if this is a reasonable definition of unusual? And as this is a subjective question, I'm going to leave it as an open and unanswered question for you to reflect on. Thank you very much for listening. Goodbye.